What's up, everybody? Thanks for coming to visit me again at another episode of Let's Ask Paul, the podcast where I, Paul Abernathy, try to answer all your pressing electrical related questions. How do I do that? You just simply go to paulabernathy.com, submit your question, and I will reply back either in an email or, if selected, it will be utilized, obviously anonymously. We won't mention your name on an upcoming podcast, much like this one. So if you've never listened to my podcast before, I go all over the place. Everybody knows I notoriously suffer from a bad case of attention deficit disorder. I'm all over the place. I love this industry with a passion. So I am all over the place on all types of topics, teaching, all different things when it comes to electrical. But one of the key things is to make sure that I answer your questions. And so that's something that I enjoy doing. And so if you've got questions, just go to paulabernathy.com and submit your questions. And you can listen to our podcasts. And we have over 1,000 episodes dating back many years on all different types of topics that are still germane today. They're still very relevant. I don't really do podcasts that are kind of locked in a time machine. They're all over the place. And they're all going to be informative for you. You may get something out of it. You may not, but again, I think it's worth the listen, and we appreciate the support that you've given us and sharing our podcast and giving us the thumbs up and the likes. It all helps on all of our platforms. I have my share of haters out there, and there's that one guy who's got a thumbs down everything I do, and he knows I know who he is because I obviously track his ISP. But again, for the fact that I don't mind, you just, go ahead. But if you like what we do me a favor, let everybody know, thumbs up, share it with other people. Let people know in your company that we have a podcast, get them listening to it. Also get our free mobile app. All you got to do is go to our website, fasttracksystem.com, fasttracksystem.com. Check it out. And you can go to the navigational link and you'll see mobile app and basically just download it. It doesn't put anything on your phone except for a link. So it's not available in your app store. You can't get it in a Google store or Amazon or whatever what is that, iPhone store, Apple store? No, you only get it from our website. So check it out. And if you don't like going to my website, there's another way you can get it. Just go to NECCHAT, that's NECChat.com, NECCHAT.com. You can download it from there as well. That's sponsored by Wix as well, so check that out. All right, so if you're coming to this episode, you saw the title. It's talking about parallel circuits. But before you listen to this episode, I want to employ you to go back and listen to the Ohm's Law episode, which I believe is episode 171 of the Let's Ask Paul series. And then you want to listen to the series circuit podcast, which is episode 172 of this Let's Ask Paul series. Listen to those first. So if you're just stumbling on to this parallel circuit podcast episode, go on and stop now and go on and go search for the series circuit one or the Ohm's Law one, because you need to understand Ohm's Law in order to be able to work an equation. And in the series podcast, I do an example of that in my long-winded style, that everybody likes, But I do it in order to break it down so that you can kind of mentally grow a picture of different equations and why we're doing what we do. So make sure you go watch those, or I shouldn't say watch, go listen to those. And maybe you're going to listen to it a couple times, get your, get a piece of paper out, jot down the equations that as I describe them, and just work it. It's just going to make you better. Or maybe you don't do that and you just listen. That's fine. Okay. Assuming you've done that and you're ready to go, today we're going to be talking a little bit about parallel circuits. Now, as I've said before, when it comes to series circuits, chances are as an electrician, you're rarely going to ever use series or parallel calculations out in the field. I mean, let's be real. If you're a residential person, you hardly will never do it. And most of the time, you may be doing, if anything, a series calculation just because of the various loads of luminaires, even though today, most of the luminaires are going to be low wattage, LED, maybe fluorescence, maybe it's CFLs or whatnot, that type of thing. So the loads wattage-wise is going to be very low. So maybe people don't do any of these calculations anymore, really, to be honest with you. But when it comes to an electrical exam, you need to understand how to do the basics of a series circuit and the basics of a parallel circuit. And you need to know Ohm's law, because in a lot of these questions, they're only going to give you certain variables, right? They're only going to give you the voltage and the amps, or they might give you the wattage and the voltage. And you're going to have to use the Ohm's law formulas with an Ohm's wheel, that in many cases, the exam gives you an Ohm's wheel. But if not, you don't want to try to remember all those. So if you're in a state that allows you for your exam to write these formulas down, then you write them in the front of your code book where you have all those code panel members. You have all that blank space there. That's a great place to write them, jot them down. Put an Ohm's law wheel there. Maybe get an Ohm's law sticker and put an Ohm's law sticker there, or something to that nature. And that is going to be a good resource for you. Now, if you're out in the field and you've already got your license, then you can jot all these things down in your code book anyway, and it's just good to have in case you need it, that type of thing. This is also a good opportunity for me to tell you that for voltage drop and things like that, we do have pocket edition voltage drop cards available over on our website, fasttracksystem.com. They're like $5.99, and that includes shipping. Check them out. They help support the show, and they have also on the backside, we show you how the 12.9, for example, or the 21.2 for aluminum, we show you how that's actually calculated, how that comes to be. So it's kind of a nice little history deal. But we also give you the formulas for voltage drop, find the maximum length, all that kind of stuff. What's the volts dropped, all that. So they're great little cards to have in your wallet, and they help support the show. Go check those out over on fasttracksystem.com. We'd love to have you get some of those. It's a two-sided card, by the way. It shows a picture on the website, 2 cards, but it's really just one card printed on both sides. Okay. All right. Anyway, that's all available. And again, we appreciate the patronage. Okay, let's talk parallel circuits. So as I told you in a previous episode, when it comes to series, there were some basic things to remember. And I don't want to rehash those, but if you remember, when it comes to series circuits, the current stays the same at all your node points, all your load points. It is the voltage and the resistance that becomes additive, okay? Now, if that doesn't make sense to you, then you do need to go back and listen to the series one. Stop what you're doing right here before you get involved in parallels. You need to go back and watch that series edition, or listen to that series edition. Trust me. And for everybody that says, Paul, I'm a visual learner, you need to do that in a video. We've got videos on this over on Fast Tracks Tube. I'm doing a podcast, so I understand. So as itchy as you have to make that kind of comment, please don't, because it won't be seen and it won't matter. Okay? I'm just telling you from the kindness of my heart. This is a podcast. So one of the things that I try to do, and I pride myself on, is trying to convey something in a mental picture that maybe will last. And that's part of the why I love podcasts, because it's a challenge to do so. All right, let's talk about parallel circuits and see some of the general rules, and we'll talk about an example and how you would solve it. A parallel circuit is a circuit that has more than one path for which the electrons may flow. So in a series circuit, it's just one continuous path, if you're buying into that kind of electron flow theory. And we are when we're trying to explain these concepts. It's not actually how it works with the electrons, but we get it. Okay? So if you think about a parallel, the electrons go out. Let's just say they go out. For simplicity, I know I'm going to have somebody on there to say, that's not how that works, Paul. I'm like, dude, then you didn't listen to the whole damn podcast, because we're talking about theory here to try to make it easy for you to understand. So when you have multiple paths parallel, and the easiest way that I can explain this to people is because we've beat it to death for people when it comes to series and parallel arcs with arc fault, is that a series arc is when there's an arc that's in series with the circuit, and a parallel arc is one that arcs across 2 conductors. Okay, it creates an arc, like an arc between the white and the black, let's say, because you damage the non-metallic sheath cable with a staple, or you have an extension cord that you crush in the door. You get me? That's an R. So there's multiple paths for it to return in a parallel. With the series, there's only one path that it has to follow. So in a parallel, there's multiple paths that those electrons, if you will, could follow. All right, so there's some givens that you have to keep in mind when it comes to a parallel circuit. And we told you these givens, again, for the series circuit, was that the current remains the same at all resistive points, and it's the voltage and the resistance that are summations, they're additive. Well, now let's look at a parallel. So in a parallel, you've got some of these rules. Now, here's what's different. Whether the current in a series is different than it is in a parallel. Listen to this. The total current in a parallel is equal to the summation of the currents in all the branches of the circuit. So the first thing that you need to remember, that you can live with remembering, is that when it comes to current in a series, it's fixed. When it comes to parallels, it's additive. Okay? Okay, that's the first thing to remember. Next rule. And in other words, if I have 3 nodes of resistance, then the resistance at node 1, three loads, and the amps at node 1 is going to be different than the amps at node 2, which is going to be different than the amps in node 3. You with me? Okay. And you add them up, and that's going to give you the total current for that parallel circuit. Okay. It's not the same as you do for the series. Okay. Series, all of the points of the resistance or wherever all the points of where the load is are going to be exactly the same current. That is not the same for the parallels. Okay. Number 2. Now here's what's similar to series. In a parallel, the voltage across any branch in a parallel is equal to the voltage across the other branches and also equal to the total voltage. So, like the current in the series, the voltage in the parallel is exactly the same at all points. So the first load, it's 120 volts, it's the same. Second load, it's 120 volts, it's the same. Third load, it's 120 volts at the same. Why? Because it's tapping off, let's say, in a parallel, it's tapping off that circuit that's coming out. And since you're putting multiple connections to it, the voltage is going to be the same at all those points. Okay. Now, the load itself can vary based on it's a hairdryer here or a dishwasher here, or I mean, you get what I'm saying, right? Not that they're on the same circuit. They're not. But come on, people. Let's just I'm just throwing you values here, okay? Relax. I know that one guy out there can't wait to thumbs down it because he said, Paul said dishwasher and a hairdryer. I'm just throwing loads, folks. Relax, chill, calm down. So we have these various different loads, and they each have different amp values, obviously, okay? But the voltage is the same on that circuit. And then, of course, the resistance is the last equation. And the resistance is the total resistance in a parallel circuit is found by applying Ohm's law to the total values of each load. Okay, so the total resistance is the total E voltage, okay, which in this case, the total E voltage was what? 120 at every point, divided by the total current, okay? And that's the total current at each point, added up, which is, again, adding all of the current, because remember, current is additive in a parallel circuit, okay? So to find the total resistance, you're going to take the voltage divided by the total current. So why is that important? Because if we have some variables missing at any one of these loads, we're going to have to use Ohm's law to find out the values at any given point. Let me give you an example. I have say I have 3 different loads that are installed in parallel on a circuit. And the first load tells me the voltage and it tells me the ohms, but it doesn't tell me the amps, which is I. So this is where you got to remember what, folks? Ohm's law. That's what I'm saying. If you have not listened or have not listened to that one before, then that's important for you to do that. Okay. So if we're going to solve for, in this case, we want to find the amps. then the amps are what's missing. We have the voltage and we have the resistance, then it's pretty easy to do, right? Ohm's law. It's 120 divided into 60, if that's what the resistance is in ohms. So it's 120. The first load is 120 volts. Obviously, it's parallel. That's the source voltage. And then it's 60 ohms of resistance. And we're trying to find what the amps are at that one point. Well, then you're using simple Ohm's law. 120 divided into 60, it's 2 amps. That's what the amps. So now we have all the variables. We have the voltage, we have the amps, and we have the ohms. Makes sense? So the first thing to remember in all that is that's how simple it is to try to remember that series current remains the same at all points, and the voltage and the resistance are a summation or additive. When in parallel, it's different. In paralleling, the current, the amps, is additive, but the voltage remains the same at all points, right? And then the total resistance is the total voltage divided by the total amperes. And that gives you the total resistance, okay? So if I had to, let's see here. If I had to do anything, let's see here. A couple other tips that we'll give you is in a parallel, the total resistance is always less than the resistance of any two branches, okay? The total resistance is going to be the less of any two branches. So give you an example of that. Let's see here. If there's a branch circuit that has the same resistance, then each will draw the same current. If the branches are in parallel, have different resistance, then each will draw a different current. Makes sense. We just showed that. And each series of parallel circuit, the larger the resistance, the smaller the current draw. Okay. So the larger the resistance, the smaller the current. Okay. So let's kind of look at an example here. Let's say I have 3 different nodes, and I'm just going to show you how you would add this up. And the 3 different load points on a parallel circuit. The first one is 120 volts, it's 2 amps, and it's 60 ohms. The second resistive point, obviously the voltage is going to be the same. We saw that. That's 120 volts. And the amps are 1.5 amps at this location. And the resistance is 80. The third location, again, the voltage is B120. The amps are 1 amp, and the resistance is 120 ohms. Okay? So in solving this on an exam, this would be easy because you're given everything. Okay? I would leave out something on an exam, so you have to do Ohm's law first to get these values, and you can do that pretty straightforward. We just did an example of the first resistive point or first load point. But here, what do? So if I ask you the question and says, what is the voltage at the source, or what is the voltage at each point of the load in a parallel circuit, then it's easy. It's 120 volts. If I ask you what the total current is, remember it's a parallel, so they're additive. So that was 2 at the first one, plus 1.5 at the second one, and 1 at the third. So it's 4.5 amps total for this parallel circuit. And then when it came to the ohms, you're like, okay, well, how do you calculate the ohms? Well, the ohms is the total of the voltage, which was 120, divided by the total current, which was 4.5. So this one's pretty simple. 120 divided by 4.5. And that gives me 26.66 ohms of resistance. So that is the total. Now, interesting. Did you notice that the 26 ohms was less than any of the resistors or the resistance totals in each one of the different loads? Remember, the first one was 60 ohms, the second was 80 ohms, and the third one was 120 ohms. And our total resistance is only 26.266 ohms. So it is less than any one of those. Okay? So that's kind of important to remember on an exam when you're seeing examples. And that's why it says that, again, in a parallel, the total resistance is always less than the resistance of any branch. So that 26.66 is less than 60, 80, or 120. So on an exam, you could probably be given four different loads, And you want to make sure that you're going to make sure that the 1 is going to be below 60, 80, or 120. So if any of those are the answers, you already ruled those out because you know that it's going to be less than any one of the resistance of any one of the other branches, okay? Or any other load. So that's one little tip to remember when it comes to the parallel, okay? Okay. So let's talk about total resistance again and break this down so we can see every little piece or every little formula that we might have. So if I want to determine the total resistance in a parallel circuit when the total current and the total voltage are unknown, right? So I have no idea what we're dealing with. All they give me is resistance. So you could get this on an exam where they draw you out 3 different resistors and they give you this. One is 60 ohms, one's 80 ohms, and one's 120. And you're like, okay, the hell am I trying to solve for here? What are we trying to do? And it wants to know what the total resistance is, but that's all it gives you, right? Okay, well, one of the ways that we can do this is if you look at it, then what did we say? One of the formula that you're going to do is you got the 1 over RT equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So this is one of your formulas you can use. Okay, so we have 3 different resistive loads here. So let's work this math. This is an easier formula to remember. When you draw it out, it's just draw a line under the 1 and then put RT. That's the total. That's the RT total resistance. And that equals to, again, 1 over R1 plus 1 over R2 plus 1 over R3. So that 1 over R1 is a process that you've got to work. That is some division that you've got to work, okay? So let's make sure we know how we're doing this. So once you write that down, so what did we have? We had 3 different loads. We have a 60, an 80, and a 120. So the first one would be 1 over 60, because that's your R1, plus 1 over 80, plus 1 over 120. So I'm going to do 1, okay, and just kind of work it out and see what we've got in total and work our math, okay? All right, the first thing that we're going to need to do is we're going to have to lay out our formula, okay? So remember what I said earlier. So it's going to get your pencils, if you have them. 1 over RT equals 1 over 60, that was our first resistive load, plus 1 over 80, which was our second resistive load, 80 ohms, and then plus 1 over 120, which is our third resistive load. Okay, so that's our 3 loads. Remember, our question wants to know what the total resistance, but we weren't given any voltage. We weren't given anything else. This is all we were given. Okay, no current. This is it. So the first thing we got to do is when you draw that out. And so we're going to go, okay, one of the easiest way to do this is to go to the highest number, which is the 120 ohms. You need to find out what is the lowest common denominator amongst the 60, 80, and the 120. Well, the easiest thing to do is go to the largest one first, and that is the 120, and just do it 120 plus 120, because that's the next one would be 240, right? Now, since we know 80 won't go into 120, so that 120 can't be the lowest denominator, and 60 does go into 120, right? 60 plus 60 is 120, but 80 plus 80 is not, okay? That would be 160, so that can't work, right? Because then plus another one would be higher. So 120 is not the lowest denominator. So we went up in 240. So I always go to the largest resistor, the largest number, and then do it times itself, or plus itself, to find out what the next one would be, and then see if the others will work into that and how many it takes to get to that. All right, so since 240 is what we'd be working on, we'll go to the first one, the 60. So we'll go 240 divided by 60, and we see that it goes into it 4 times. So you write that down, 4. The next one is the 80. So I'm going to go 240 divided by 80, and we see that it goes into exactly 3. So I'm going to write that down, 3. And of course, the 121 we know is twice to get 240, so that would be a 2. So you add those up. So that's 4, 5, 6, 7, 8, 9. Okay, so underneath the bottom is your lowest common denominator. So we're rewriting this formula now, and the lowest common denominator is 240. So it's going to be 9 over 240. Okay? So that's our new equation, 9 over 240. And now what you do is you do what's called cross multiplication. So you have the 1 over RT, and then you had the 9 over 240, which is what we just worked out. And so you do the cross multiplication. So 1 is going to do what? 1 times 240. So now the 240 goes on the top. And since the 240 now goes to the top, the 9 goes to the bottom, and you just simply divide the 240 divided by 9, and that is 26.66 ohms. Okay? So a summation of that is, again, once you know each of the resistive loads, then it's 1 over 60 plus 1 over 80 plus 1 over 20. Find the common lowest denominator. In this case was 240. And then it's how many 60s went in to get to 40. So that was on the top, the 1 is replaced with 4. And then how many 80s does it take to go into 240? 3. So that goes on the top and replaces the 1. And then how many 120s went into 240? Well, 2. So that replaces the 1. So your new formula looks like 1 over RT equals 4 plus 3 plus 2 over 240, because 240 was the lowest common denominator. And then really what you do is you can cross multiply, but really in this case, you just flip it. And then it's just 240 divided into 9, and that is 26.66. And that was your ohms of resistance. And as we said earlier, you will notice that the 26.66 is less than any one of the actual resistance values that we have. We had a 60, 80, and 120. And obviously the 26.66, like we did before, is less than any of those. So that what might be a trigger for you on an exam. Okay. All right. So one of the other things that I like to throw out is, what if you have an equation, and we're talking parallels here, where all of the resistance or all of the loads that are installed in parallel are exactly the same, right? So what if we had an example where you have three loads, the resistance value is 120, 120, and 120? Well, that's easy, because what you do is, if that's the case, then how to find the total resistance is to do the resistance, okay? And remember what we said about parallels when it came to resistance? You remember? Remember total resistance? Okay, so we're taking the resistance, and what is the resistance in the equation? RT equals R over N. So we take, since they're all the same, we take any one value in resistance, so we take the 120, and we divide it by the number of resistors that we have, or loads that we have. And this case was 3. So it's simply 120 divided by 3. And so the total resistance for 320 ohm loads in a parallel is 40 ohms. Now, again, that seems like it would blow people's mind, but it isn't when it comes to parallels. And it's different, right? When we talked about series in our previous podcast, people are like, well, the resistance is what? RT equals the sum of R1 plus R2 plus R3, but that's not how it goes here. You don't go 120 plus 120 plus 120. No, they're paralleled out. So that's why we use the formula RT equals R over N, and the N being the number of resistors if they're all the same. So if you get a question and they're all the same exact resistance, and they want to know what the total resistance is, and it doesn't matter, they're not giving you voltage, they're not giving you amps, who cares? That's not what the question would be asking you. It just wants what's the total resistance. So you can still calculate that out. Since they're all the same, you just take the 120 divided by 3, and that's 40 ohms. So that is your total resistance for the entire circuit. Yes, it's 120 at each load, but it is 40 ohms of total resistance. Okay. All right. So one of the common questions on an exam is they want to know what the total resistance is, and it's just giving you the resistance, and they give you 2 values in a parallel. So think of this as 2 straight lines and then 2 perpendicular loads running between them. And both of these loads one is 40 ohms and one is is 80 ohms, okay? So again, if this was the same two, they both were 80, then that's easy, right? You just 80 divided by 2, and it's 40 ohms, right? But it's not the same, okay, when it comes to this because the loads are different. One is 40 ohms, one is 80 ohms. So there's a formula that you use for this, and I'm going to tell you the formula. You can pause and write this down or come back to this episode. It's right at about 30 minutes and 54 seconds into the episode. It's R1 times R2 divided by R1 plus R2. Really simple. And all you do is work the two. So the first one, so if one of the loads was 40 ohms and one was 80 ohms, let's work the top first. R1, let's say, is the 40 ohms and R2 is the 80. Simple. So it's 40 times 80. And that's your top value. That would be 3,200. The bottom one is R1 plus R2. So think of this, multiplication first and then addition, okay? So then it would be 40 plus 80, and that is 120. So it's simply 3,200 divided by 120. So 3,200 divided by 120, 26.66 ohms, and that is your total resistance. And guess what you noticed? It is still less than any of the resistors here, any of the resistance loads here. The lowest one was 40. It's less than that. It's 26.66. So this helps you, if you're an exam taker, to narrow out some of the obvious ones that are not going to be the answer. So even if you can't figure it out, you could probably use a process of elimination and get you down to the best possible answer, okay? Okay, before I leave this episode, I do want to show you another way that we do this when you have multiple parallel circuits. And I showed you the way to do it earlier with a common denominator. There's another way to do this, and I want to show you this one, so bear with me. Using that exactly the same formula, because you can choose what you want. I showed you the shorter method to utilize, but I'm going to show you the same method to do it, but this is going to be a little bit longer one. Okay, so remember that formula that I used earlier? 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. You with me? Okay. So in how we do this, one of the ways that you can do this is to work it out. So remember what we said, those three loads were, or resistance was 60, 80, and 120. So let's solve each one. So that one would be, the first one would be 1 over 60, right? So let's work that one real quick and write it down. And again, if you're using this method, you want to write down every decimal point. Every space after the decimal point. So let's do 1 divided by 60. And that is, wow, that gives you a lot of decimal points. So the first one is 0.01666666. So for your math, folks, that's 1, 2, 3, 4, 5, 6, 7 sixes, okay? So it's 0.01 and then 7 sixes, okay? Just trust me. You're going to have to use the entire value in order to get it close to the version that we did earlier, which was the common denominator version. All right, so the next one was 1 over what? Well, the next one was 1 over 80. Okay, so let's do that one. So let's do 1 divided by 80, and that is 0.0125. Okay, that one was easy. Only 4 decimal points. Good. Our places. All right, so the next one is 120. So we do 1 over 120. And that one has quite a few spots. Okay, let's do this again. 1 divided by 120. Okay, so we'll write that down. 0.008333333. So there's 1, 2, 3, 4, 5, 6 threes. So it's 0.008 and then followed by 6 threes. Okay, these are the total numbers, and I'm going to show you why you would do this. Now, typically we would go to 4 spaces, and it's not going to equal the same as the denominator value, but I just want to show you how we could do it this way. All right, so now what you do is you add up all of the denominators. That's across the bottom. Okay, so that is the 0.01666666666. So I'm going to do it here. So it's 0.016666666 plus 0.0125 plus 0.00833333, and that gives me a total of 0.037499999. Okay, so that is 0.0374 and then followed by 5 nines. Now, I'm going to divide 1 into that. So we go back to the formula. So it's 1 over this value number. So I'm going to finish it out. I'm going to 1 divided by 0.03749999. And that gives me 26.66666. So we can use 26.66. So in order to make it match the denominator the way I did it earlier, you have to use all of the values. And the reason I'm bringing this up is because you'll have people out there that say, well, you only have to go to the 4 spaces. And that's true. But that won't match the denominator value. And for the end of the day, for the real world, it's fine. 4 spaces should be more than enough to find out what the resistance is. But if you want to get it exact, then you use all of the values from your calculator. Okay, and that's what we did. Ultimately, if I had done it to the 4 spaces, then it would have been slightly different. It wouldn't have matched the one we did earlier at 26.66. It would have been more like 26.7 or whatever. It's close enough, okay? But I just wanted you to see the difference. You can certainly use this formula to do like I did and work it all the way out, or you can do the version we did earlier, which is the common denominator version. Hey, it's whichever version that you feel comfortable with. And maybe you have a situation where you can't figure out what the common denominator is. And I kind of gave you tips on how to start out, take the larger value and use that one, and then see if the others will work into it. But if not, you can do it this long method. It just takes a little longer. But either way, that's examples of how you can find the total resistance when they don't give you the voltage, when they don't give you the amps, and this is all they give you. All they give you is the resistance, okay? So hopefully that helps you out in case you get one of those type of questions on an exam, okay? All right, folks, that's it. Hopefully you got something out of today's episode. We're going to do another episode, the last one in this series of Let's Ask Paul's, dealing with series parallels. We're going to do a quick one on combinations to show you how you work from a series down to a parallel. From a parallel down to a series, and because the series are easier to work. And that's what we're going to cover in the next episode, okay? All right, again, these can get complicated. If you want to watch a video on it, then you get a subscription to our Fast Tracks tube. We have videos on it that shows examples on the screen. We even have a video where you sit in on us on a Wednesday night where I talk about these things, and it might help you. Again, probably on an exam, you might only have 1 question, 1 or 2 questions. So I wouldn't die on this sword, but it's important that you understand these basic concepts, okay? All right. Remember this episode, folks. I believe it's 173. I'm not sure. Don't hold me to it. If you have any questions, you can always go to paulabernathy.com and submit a comment, ask a question based on an episode. Just be very detailed in your question because I'm not going to go back and listen to the episode to be able to answer your question, okay? I don't have the time for that. Till next time, folks, stay safe. God bless.